of the experiment. So if you're going to look at the experiment, chapter 4 covered a lot of the experiment. I think starting with experiment 4, 5, 6, 7. All of them, okay, are topics of chapter 4. In fact, I would say chapter 4 is the one that covered a lot. So I'm not sure if we can finish chapter 4 today, but we will try our best, okay, to do so, okay? Because if you're going to look at the topic of chapter 4, it's all about chemical reaction. And if you look at this so-called chemical reaction, that is the heart of chemistry. So chemistry is all about chemical reactions. Okay? Chemical reactions are chemical chains. So if you're going to look at this, some of these chemical reaction can be simple. Some are, we could say, dramatic, that is accompanied by some sort of an explosion, some sort of a forest fire. Okay? So we could say there's a lot of stuff that is happening around us that we could say is about chemical reaction. And they said chemistry advanced because of the knowledge of the so-called chemical reaction. So if we're talking about chemistry 100 years, there's only few chemical reactions that are known. But once scientists starts to synthesize, so what they do is they just do chemical reactions. Okay? So in this topic that we have today, we're going to talk about electrolyte. We're going to talk about the different type of chemical reaction, how to write a chemical reaction from the complete until the what we call net ionic equation. We're going to talk on precipitation reaction, acid-base reaction, redox reaction, and we're going to have calculations with regards to solution and stoichiometry involving chemical reaction. So we could say this is just a continuation of chapter 3. Okay. Now, why do we need to have to include here some sort of a solution chemistry? Because if you're going to look at the chemical reaction, most often they happen when they are in a solution. Have you ever seen a chemical reaction that is made up of what? Both solid particles reacting with one another. So usually one of them should be in aqueous form, or we could say in a solution form. And it can react with the solid or another solution. Okay? So chapter 4 is all about stuff that is happening around us. So the first topic that we could say is having something to do with electrolyte. Okay? So when we're talking about electrolyte, these are substances that dissolve in water to give an electrically conducting solution. Okay? So why do they conduct electricity, or why do they have the ability to conduct? Is because of the presence of the ions. So if you have an electrolyte, these are just substance that dissolves in water to give on electrically conducting solution. And that is covered in experiment 6 about the so-called conductivity. Okay? So conductivity is just a measure if a solution can conduct or can conduct what we call materials. So there are three terms that we use for an electrolyte. We can say it's a strong, weak, and non-electrolyte. So how do we differentiate one from the other. So when we have a strong electrolyte, it dissolves to produce ions. The dissolution of the compound to produce ions, we could say, is 100%. So what does it mean? If you have a salt, when you put it in a solution, that salt separate into ions. So for instance, if you have NaCl, if you're going to dissolve it in water, okay, it will form Na plus and Cl minus. So there is 100% complete ionization. So your salt separate into a positive charge and a negative charge. And that is a strong electrolyte. Okay? So when you have an ions, it can conduct electricity. So one way to determine if it's a electrolyte, a strong electrolyte, is doing the light bulb test. So usually, if you have a light bulb and you dissolve, okay, the, I just want to pass that thing. And if you dissolve, okay, a wire that connects to the bulb, what happens is the solution will be able to conduct electricity. So what happens is you're going to produce a strong, intense light. Okay. Now, some of these materials don't undergo 100% ionization, but to some extent, they produce some ions, and you call them weak electrolyte. So when you have a weak electrolyte, to some extent, some of the given compound dissolves in water to give relatively small amount of percentage. And if a strong electrolyte you undergo 100% dissociation, we could say weak electrolyte is less than 100%. Sometimes even around 10% as the maximum. Okay? You will still be able to conduct sorry for that, the light bulb, but compared to the strong electrolyte, okay, it is dimmer. The one in the weak electrolyte is dimmer compared to the one in the strong electrolyte, which is brighter. Okay, so just telling you that only a small amount of the ions dissociate. Okay, so if we're going to look at the specific example of, let's say, strong electrolyte, we can put there the soluble salts, which you're going to learn about today. And then you can also include here the strong acids and bases, which you're going to learn also today. Okay, in the weak electrolyte, we can include the weak acids and the weak base. So what you're going to learn about the strength of the acid is just its ability to ionize or dissociate. Okay. Now the last one that you have here is what we call the non-electrolyte. So when you have a non-electrolyte, what happens if you dissolve them in solution or in water, it will not give you any ions. It will remain as is. So if you're going to do the light bulb test, what will happen? It will not light up. Okay? An example of these non-electrolytes are the so-called molecular compounds. Pure water itself does not conduct any electricity. Pure water is non-electrolyte. But what makes water allowed to what we could undergo or conduct is the presence of some ions. And usually you have a lot, especially if you have the so-called tap water. But if you have pure distilled water, it will not conduct electricity. I think I have some questions on that in your experiment 6. So my suggestion to you while you reviewing this portion here, you can start doing the experiment. 4, 5, 6, and 7. And it's going to help you when you take your quiz later this week. Okay? Now, we go to those things that we said soluble versus insoluble. So anything that readily dissolves, okay, any compound that readily dissolves, we call them soluble compounds. So what does it mean? You have some of these compounds, you put it in water, it's gone. It's dissolved. It's gone because it turned into ions. However, there are some compounds that if you put them in water, you can still see, okay, their presence. So these compounds don't dissolve in water. So we can call them insoluble compound. Now, the term that we have right now, soluble and insoluble, we could say is qualitative in nature. Because when you go to Gen Chem 2, you will see that what we call the insoluble compound, they are soluble to some extent. It just happened that maybe this is grams per liter when they dissolve in aqueous solution, while those insoluble compounds are micrograms to milligrams per liter. But for the sake of simplicity today, okay, we say anything that doesn't readily dissolve are soluble, and the one that dissolve very little are insoluble. Okay, so how do we know the substance that are soluble and the substance that are insoluble? We have the so-called solubility rules. Okay, now you ask yourself, do we need to know this thing? I'm going to put these rules in your quiz so you don't need to memorize them. Okay, so if we have the solubility rules, all we need to do is look at the statement, and if we're given a sample, we just identify that compound and see if there's a statement that will dictate their solubility. So the first rule in the solubility rules, group 1A, so these are the group 1A in the periodic table, and ammonium compounds, they are soluble. So if we could say our cations are any of the group 1A, like, if I'm not mistaken, lithium, sodium, potassium, and all in group 1A together with NH4 plus, because they are what we call cations, positive charge. When they are present, you can say that compounds are soluble. Okay? Now, when you have acetates and nitrates, these are the NO3 minus and the CH3COO minus. So you could say that they are also soluble, whatever the cations that they have. Third statement, most chlorides, bromides, and iodides, in short, the halides, the one that is in group 7A, they are soluble except when they are silver, mercury, and lead halides. So if there's a presence of silver, mercury, and lead, so you expect their halides to be insoluble. Okay? And then you have your most sulfates are soluble. The exceptions are calcium sulfate, strontium sulfate, barium sulfate, silver sulfate, mercury sulfate, and lead sulfate. So, as you could see here, okay, the same cations that you have for the halides, they will also give you insoluble sulfate. And in addition to that, calcium, strontium, and barium, which are usually what? Group 2A. Okay? But as I've told you, you don't need to memorize, but you need to understand what these statements mean. So if you're given strontium sulfate, you could say it is insoluble. Because question that you will have here, which of the following are or is are soluble? Which of the following are or is are insoluble? And you're going to need this to dictate whether you're going to have a precipitation reaction. Okay? So all of this statement will be made available to you in one of the items that you have in the quiz. So you don't need to worry. All you need to know is know how to use them. Okay? And then we have number 5, most carbonates are insoluble. And the exception here are what we have in statement 1. Okay? I think if you're going to look at 5, 6, 7, you're going to apply here also statement 1. Most carbonate, phosphates, and sulfites are insoluble except group 1A and ammonium compound. And then most hydroxides are insoluble except group 1A, including the ammonium hydroxide that you have, which is just ammonia, and the group 2A. So these are the ones that are soluble. Okay? So let's try to test. Just type whether it is insoluble or soluble. You can just put S or I in each of them. So try to answer. So you can have an idea some of the questions that will be asked in your chapter 4 quiz. Mercury chloride. What can you say about mercury chloride? S or I? What is mercury chloride? Is it an S or soluble or insoluble compound? Anyone? So mercury chloride, all chlorides are soluble except silver, mercury, and lead. So this is insoluble. Ki, potassium is group 1, and then you have iodide, so that's soluble. Lead nitrate, you have here nitrate. So what did we say with the nitrate? All nitrates are soluble. And then sodium bromide, what statement is applicable here? So this is a group 1, and you have a bromide. So all group 1 are soluble. So that means this is also soluble. And then you have here a carbonate. So you say most carbonates are soluble. The exception is group 1A and ammonium. And calcium is not group 1A, so most likely this is insoluble. And last but not the least, sodium phosphate. Again, you have the sodium, a group 1A. So you could say, okay, this is also soluble. So ask yourself, do you think you can answer these questions in the exam or in the chapter quiz that we have? Because those are the type of questions that we have here. But you will have the solubility rules. You think everything will be okay? Huh? Let me know. So you don't need to memorize because you have the table with you. So you will have questions like this on what we call your chapter quiz, which you're going to take between Thursday and Friday this week. Okay? Now, the next thing that we're going to do, okay, equation. So when we have an equation, this is where we put the reactants and the products. Okay, we discussed about chemical equation in chapter 2. So when we have a molecular equation, we're going to write a chemical equation in which both the reactants and products are written like molecular substance, even though, okay, they may exist as solution in ions. So whenever we have the molecular equation, we can put solid, liquid, gas, but in addition to that, we have the aqueous. So this refers to solutions with water as the solvent. So for instance, if we have this silver nitrate reacting with NaCl, you produce silver chloride and sodium nitrate. So although the silver nitrate and NaCl and NaNO3 exist as ions, so what does it mean? Okay, this doesn't exist as aqueous. This doesn't exist as aqueous. This doesn't exist as what we call as it is. The one that it exists is if you're going to separate the sodium ion from the chloride ion, the silver ion from the nitrate ion, and the sodium ion and from the nitrate ion. But they're written that we're going to write them as compounds in the molecular solution. Okay. So what are we going to do here now is maybe we can make it into what we call the complete ionic equation. So what is a complete ionic equation? How is it differ from a molecular equation? So here, anything that exists as ions, you have to break them down. You're going to write them as separate ions, especially the strong electrolytes. Okay, so what does this mean? We're going to separate this into silver and nitrate ion, and this one into sodium ion and chloride ion, and this one as sodium ion and nitrate ion. So we're going to write those that exist as ions, compared to the molecular equations where we just write those ions in aqueous solution as compound and just put the symbol AQ. Okay? Now, what happened to those that exist as ions in both sides? So for instance, if you're going to look at here, when silver ion reacted with chloride ion, you produce a solid or what we call a precipitate. So what happened to these ions? This one, nitrate ion, sodium ion, that you can see on both sides. This is what we call spectator ions. So when we have this spectator ions, okay, you can find them on both sides as ions. When I say both sides, reactants and product side. So a spectator ion in an ionic equation, it does not take part in the reaction. It is there just like a spectator. It's just looking at the reaction. Okay? So if you are asked what are the spectator ions in this reaction, your answer will be the sodium ion and the nitrate ion. Okay? So what happened? So when we have this total ionic equation or the complete ionic equation, we included the spectator ions. But since they are present in both sides, so you have it here, you have it here, you have it on this side, you have it in this side, you can cross them out. And when you cross them out, the one that is left, the one that participates in the chemical reaction, okay, you will now have the so-called net ionic equation. So what type of questions that you're going to expect from here? Given this reaction, identify the spectator ions. Given this molecular reaction, write the ionic equation. Now, what guides you to write the net ionic equation? That's where your solubility rules comes in. Because you may ask yourself, why is silver and the chloride that precipitate? Why is it not the sodium and the nitrate? So we all know sodium is group 1A. So based on the statement, all group 1A are soluble. And we all know that nitrate has a statement that all nitrates are soluble. And if we go with the chlorides, they have a statement also, all chlorides are soluble except silver, which is one of the species, lead, and mercury. So those are the type of the questions that you're going to expect. Okay? So maybe try to practice. Maybe we can have another example here. So the one that an underline here, that's the one, or the one that was in squared here, that's the one that are what we call participants in a net ionic equation. The one that was crossed out, that is your spectator ions. Okay? So decide whether the following reaction occur. KBr reacting with magnesium sulfate. So how are we going to do this? So you separate them into the respective ion and then try to mix up and determine if the exchange of the ions result in a precipitate. So how does you determine the precipitate? Again, you go to the solubility rule. The one that will form insoluble substance, that's your precipitate. So based on this, you may end up forming potassium sulfate or magnesium bromide. And if you're going to look at the solubility rules, both of them are soluble. And if both of them are soluble, there will be no reaction. Did you get that? Anyone? So what happened when you mix both of them? Nothing happens. So that means there's no chemical reaction. And it is dictated by the solubility rules. Let's try another one. So you have sodium hydroxide reacting with magnesium chloride. Again, you're going to break them down, okay, into cation and anion, and then you swap the partners. So Na will mix with the Cl, and then magnesium will mix with the hydroxide. So you form these two compounds. And based on these two compounds, you predict the solubility. You have the statements of the solubility rules. So based on this, your NaCl is soluble because you have the group 1A, but your magnesium hydroxide is insoluble. So that means there is a chemical reaction. And you can write, okay, the three forms of molecular, total ionic, and net ionic equation. So maybe what you can do is you start with the molecular equation. And in the molecular equation, you have to make sure it's balanced. So this is the molecular equation. And what you're going to do, you look at the aqueous and you break them down into ion, giving you 2Na plus and 2OH minus from 2NaOH. And then in the magnesium chloride, you have magnesium 2 plus and 2 chloride. And then in the 2NaCl, you have 2Na plus and 2Cl minus. And then you have there your magnesium hydroxide that is insoluble. Now, question that may be asked to you, which of the following are the spectator ions? So you're going to look at here. Okay, which one is present in both sides as ions? So you have there your, I'm just showing you the breakdown that you have there. You have Na in both sides, and you have Cl on both sides. So you can say right away, sodium ions and Cl ion are spectator ions. So the Na plus and the Cl minus are the spectator ions. So question, because I have questions like that in your exam, in your quiz. You know, I want everyone to do well in the quiz. That's why I'm telling you already what you expect in the quiz. And if you're going to write just the net ionic equation, what you're going to do is you're going to remove the spectator ions and any species that's left there, okay, are the one that participate in your net ionic equation. Okay? Questions so far? Now, I leave this up to you how you're going to write the molecular, the ionic, and the net ionic equation. I'm not sure if I answered it in my other, we could say, video that is available in YouTube. But I just want you to practice how to do or to write the different equations once you're given the reactants. Okay? So how many questions do we have so far? I mean, we have the solubility rules and then writing the different equation. So what we go now is the type of chemical reaction. Precipitation reaction, that's what you did in experiment 4. Acid-base reaction, that's what you did in experiment 5. Oxidation reactions, that's what you're going to do in experiment 7. That's why I'm telling you, okay? So it will be a meaningful, we could say, preparations for your quiz. I would suggest you do experiment 4, experiment 5, and experiment 7, including experiment 6 is more on conductivity of solution. Okay? If you're going to do this experiment before you take the what we call the quiz, you have a better chance of doing well in your quiz. Okay? As I have told you, you can submit well ahead on your lab reports. The only one that we need to get on a particular time are the quizzes, the quiz that is scheduled on a given day. Okay? So, what are these types of chemical reactions? How are we going to identify each of them? How each one of them are different from each other? So the first type of reaction, which we already discussed based on the solubility rules, is the so-called precipitation reaction. So in a precipitation reaction, you have a solid ionic substance forms from the mixture of two solutions of ionic substances. So all you need to do is solubility rules. The one that formed the insoluble substance, that's what we call a precipitate. A precipitate is an insoluble compound that is formed from soluble substances. So you mix them, you form a solid. So you have there a precipitation reaction. Acid-base reaction, this is the reaction that involves the transfer of a proton between reactants. So we could say this is just a proton transfer reaction. So proton is in the form of H plus. How do you know an acid-base reaction? You have an acid and you have a base as your reacting species. And as we go on, you will know what are those acids and what are those bases. Okay? Now, redox reaction, okay? These are the reactions that involves the transfer of electrons between reactants. So this has something to do with the electron transfer. And for you to determine whether you have a redox reaction, you have to know the concept of oxidation number that we're going to discuss today. Okay? So let's go with the first one because we have started already with the precipitation reaction based on the discussion that we have. So this is just the formation of a precipitate, and a precipitate is an insoluble solid compound formed during a chemical reaction in solution. What do you need here? Your solubility rules. So anything that will form insoluble compound, you have a precipitation reaction. Okay? So predicting precipitation reaction, you predict the products. The same thing that we did today. You have two species and you are asked if you mix them, if they form. So you separate them, each of them into a positive ions and a negative ions, and then you exchange with one another. And then you have to predict if the products that form, okay, will precipitate. Will it becomes a solid, a liquid, a gas, or an aqueous solution? If all products are aqueous, just like one of the example, there is no reaction that occur. Okay? So the next thing that we're going to do is acids and bases. So there are a lot of definition about an acid and a base, but we're going to tackle only two of them. The one that is defined by Svante Arrhenius and the one that is defined by Bronsted-Lowry. So when we have the definition of Svante Arrhenius of the acid, it's just a substance that produces hydrogen ions when it dissolves in water. So when you have an H plus that is released or produced when it dissolves in water, you have the Arrhenius acid. Now when you have a substance that produces hydroxide when dissolved in water, you have the Arrhenius base. So there's a story that since this is part of his dissertation, his committee doesn't understand what he's talking about. But his dissertation became the basis for him to be awarded with the Nobel Prize in 1907. And right now, the concept of acids and bases that bear his name is still being studied, just like what we're doing today. Now, the narrow definition of your Arrhenius base force other people to define acids and bases, because if you have this definition, ammonia cannot be considered as an Arrhenius base because it doesn't have hydroxide. Okay? The Arrhenius base that you have there are just all that contains hydroxide. So because of this, Johannes Bronsted and Thomas Lowry expanded the definitions of acid and bases. And they come up with a very simple definition of an acid and bases. So they define acid as one, okay, that donates proton. So we could say this is the proton donor to another species. So what is that proton? H plus. Bronsted-Lowry base, on the other hand, is any species that accepts a proton from another species in a proton transfer reaction, and we could say that's your proton acceptor. So what does this mean? Whether when you look at the reaction, all you need to do is find the one that loses the H plus, and that is your acid. And then on the other hand, if you want to determine the base, all you need to do is find the one that got the H plus after the reaction. But you're going to tackle more about acids and base, including calculation when you go to Gen Chem 2. Okay? That's two chapters there that deals with acids and bases. But for today, we're just going to look at the concept of what is an acid, what is a base, what is a strong acid, what is a strong base. Now, in every acids base sample that we have, I always put the everyday materials around us. So when you have household acids and bases, so you have here sodium hydroxide, which is a Drano, Malax, that's magnesium hydroxide. So both of them are bases. Now for the acid, you usually have an acid with the name acid in it, like acetic acid, acetylsalicylic acid, and citric acid. So if you're going to look at this, what happened? Most of the acids are the food that we ingest. Most of the base are cleaning material, right? So those are the everyday household examples of acids and bases that we have. I don't know if you realize it. If you get too much to eat, you get what? Hyperacidity. And what do you take? Tums or the so-called antacid. Okay, when you say hyperacidity, too much acid. Why too much acid? Because as food releases acid. And if you have too much food, that means it's going to release a lot of acid. Now, there's also the use of the so-called acid-base indicator to distinguish whether you have an acid or base solution. So all you need to do is a color change that it undergoes. So the example that we have here are the cabbage. So usually the purple cabbage, they contains anthocyanins that gives you colorful solution at different pH. So it's due to the presence or absence of H plus at different pH in the so-called anthocyanins. Now, let's look at the term strength. Of acids and base. Why do we have the strong acid? Why do we have a weak acid? Why do we have a strong base? And why do we have a weak base? So whenever we have a strong, that means it undergoes 100% dissociation or ionization. If it's a strong acid, that means when they dissociate, this don't exist as is anymore. They will now exist as ions. Hi, HBr minus, HCl minus, H plus, NO3 minus, and then H plus, HSO4 minus. So they undergo 100% dissociation. That's a strong acid. Now, if you have a weak acid, they just undergo dissociation to a certain extent. Now, you may ask yourself, Professor, do we have to memorize them? Now, here's the thing. There's only 6 strong acid. In some book, there's a 7th strong acid, and that's just one less oxygen of this. So these acids that are listed here, those are just the strong acid. And if it's not listed there, 100% you can say that it is weak acid. So what can you say? Okay? And if we're going to look at this one, HCl, HBmR, HI, they are in one group in the periodic table. You have the F, the Cl, uh, the Br, and the I. So all of them are, we could say, strong acid except the HF, which is weak acid. Okay? So how can you see the difference between a strong acid and a weak acid? So for instance, if we have this macroscopic level of a strong acid and a weak acid, if you're going to look at the acid here, there's 100% dissociation. So they either exist an H3O plus or a Cl minus. So what we get here, HCl plus H2O. So what happened? Okay, the HCl donates its proton to give you H3O plus. And in the same time, since it lost its proton, you produce Cl minus. So that's what it exists at the end. Now compare it to HF. If you're going to look at the illustration here, okay, look, most of them remain as HF. Only one of them dissociate to give you an H3O plus and F minus. This one and this one. So as you could see, it didn't undergo 100% dissociation. Strong base, on the other hand, the same definition. Okay? The one that undergo 100% dissociation, those are strong base. And again, there's only a few of them. The strong common bases, we could say, are just the soluble hydroxides of group 1A and group 2A. So if they're not there in group 1A and group 2A, most likely they're weak. And I would say all strong bases are the one that contains hydroxide, because in the weak base, only a small portion ionize. It is present primarily as molecules and partly as ions. Okay? So if the base is not strong, or if the base is not listed in one of these hydroxide, most likely it's a weak base. So ask yourself, do you think you can answer questions like this? Which of the following is a strong acid? Which of the following is a strong base? Which of the following is a weak acid? Which of the following is a weak base? So maybe, okay, try to answer it now. I'll give you 2 minutes to do that while I rest my voice. Because those are the questions that you're going to ask. So you're asked to classify them as either strong or weak acids or bases. So please do it. You can type your answer in the what we call chat. I'm just going to get some water. Somebody type their answer. Okay, letter A, it's a strong base. Uh, K is a soluble group 1A, and you have an hydroxide there. So that's a strong base. Letter B is a weak acid because it's not listed as one of the strong acids, so it's weak. Letter C is a weak base. Anytime you have an NH2, that's an amine or an ammonia derivative, so it's a weak base. And letter D is a strong acid because it's listed as one of the strong acid. So do you think you can answer a question like this? Sure points? Okay. So practice. Okay. Now, another thing that you have is this term polyprotic acid. So when you say polyprotic acid, these are acid that has two or more acidic hydrogens, or anything that has more than one acidic hydrogen. So for instance, if you have sulfuric acid, we could say that's a diprotic acid because it has two hydrogens per molecule. When you have a phosphoric acid, then that's a triprotic. And both of them are polyprotic acid. Okay? Now, neutralization reaction. When does this happen? So this is a reaction of an acid and a base that results in an ionic compound, which is usually a salt, and possibly water. So if I have a reaction like this, NaOH plus HCl, okay, so I can say they're both aqueous. So when you react them, you're going to produce NaCl, which is aqueous, and water, which is a liquid. So that is an example of a neutralization reaction. Acid, base, salt, water. Now, we have discussed earlier the molecular, the total ionic equation, and the net ionic equation. We can apply it here also. So for instance here, write the molecular, ionic, and net ionic equation for the neutralization of sulfurous acids by potassium hydroxide. So how are we going to write this equation here? So the same thing that we have earlier. So we have here H2SO3, which is aqueous, reacting with KOH, which is aqueous. And the question that we can ask ourselves, what could be the possible products? So what do we do is we just exchange them. So we have here an H plus and an SO3 minus, 2 minus, and we have here a K plus and an OH minus. So that means one of the product that we have here is water. And the other one would be K2SO3. And we could say we need two of this thing here because there's two potassium in K2, okay? And this also means that we have two here. To compensate for the two hydroxide that comes from potassium hydroxide and two water that comes here, or two hydrogen that comes from H2. Now, this is your molecular equation. So how are we going to make them into ionic equation? So you have to identify here which dissociate into ions. So you need to identify the strong acids and bases and the weak acids and bases. So usually if you have a weak acids and bases, they don't really undergo dissociation. They only undergo dissociation in certain extent, but in this type of reaction, they will remain as not dissociated. So which of them will dissociate 100%? I would go for this one because this is a strong base. I can also go maybe for this one because this is a salt. But this one is a weak acid, so I can maintain it as is. They won't dissociate because they're weak acid. But I'm going to separate 2K plus and 2OH minus. Why? Because they're both strong base. They come from a strong base. So when you have a strong base, they will dissociate. If it's a weak acid, they can maintain as is. Okay? Water will remain water because it's a liquid. And potassium sulfide here, we can separate this as 2K plus aqueous plus SO3 2 minus aqueous. Okay? Because they're salt, they can dissociate. So the next question that I will ask you, which are the spectator ions? Anyone? Is there a spectator ions? How do we define spectator ions? They exist as ions in both the reactant and the product side. So the question that I want you to answer, is there a spectator ions in the reaction or in the equation? So all you need to do is find a species or an ion that is common on both sides or can be found on both sides. In this case, what do you see? This one and that one. That's all you have. So that's your spectator ions. So if you're going to write the net equation, it's H2SO3 aqueous plus 2 hydroxide producing 2H2O plus SO3 2 minus. So see how it differed from the precipitation reaction? It's most likely like what? A displacement. The hydroxide, okay, displace the sulfide to give you water and sulfide. So again, question that you can be asked here is, what is the spectator ions? And write the net ionic equation. Ask yourself, can you answer the question? And please don't be shy to ask question. You can always ask question, but just don't ask question when it is already what? 2 to 3 hours before the deadline of the quiz. Because usually I the latest email that I can read is usually 9 p.m. in the evening. So if you go beyond that, most likely I will not be able to get to give you a reply. Okay. Now, some of these so-called acid-base reaction, it can involve gas formation. Like example here, when you react an acetic acid from the vinegar with carbonate or sodium bicarbonate, what you're going to produce is CO2 with water. Okay? So some salts, when treated with acid, they produce a gas. Typically, this includes the sulfides, and the carbonates. They behave in this way, producing H2S, SO3, and CO2, respectively. Okay? So if you're going to do this volcanic eruption that they call vinegar producing, reacting with baking soda, you're going to produce CO2 in that reaction. And the other, we could say, general equations that we have here is if this one. You have an Na2 reacting with HCl to produce you NaCl and H2S. Okay? And then you have Na2CO3 reacting with HCl. It's going to produce you, if you're going to look at what is really produced is this one. And what happened to this, it will break down to give you H2O and CO2. Now, I want you to convince yourself that when you add this with this one, it will give you this compound. It's the same thing that you have this one. It comes from here. And what happened when you react, when it's formed, it's breakdown to give you H2O and SO2. Okay? Then I have here an example on how to write equation that has the gas formation. So all you need to know, I think, is this one. If you have a carbonate or sulfide, most likely they will form into gas in the form of CO2 and SO2. So you are asked here to write the molecular ionic and net ionic equation for the reaction of copper carbonate with HCl. So what do we produce here? You produce copper chloride. So that means there's two of these things that we have here. So this is aqueous. And what do you produce? H2CO3, which is going to break down to give you H2O, which is liquid, and CO2, which is gas. Now, the question I'm going to ask you is which one will dissociate or undergo ionization 100%? Will this undergo ionization, copper carbonate? Or from the original equation, copper carbonate should be S. So that's my mistake there. So usually, since it's solid, it will remain solid. HCl being a strong acid, it will give you what? 2H plus aqueous and 2Cl minus aqueous. Why? Anyone know the reason behind there? Because it is a strong acid. So it's undergo 100% dissociation. It ionizes. Copper chloride, yes, since it is an aqueous solution, so you have here copper 2 plus and 2Cl minus. While the rest, they will not dissociate. H2O will remain as H2O and CO2 will remain as gas. So the next question that can be asked here, what is or what are the spectator ion or ions? What is your answer? What is the spectator ions here? Hmm? So you have to find the ions that is present on both sides. So in this case, you have what? The 2Cl. Okay? Oops. I want you, if you got the questions like that, to nail the answer. And whatever's left there after you remove the spectator ions, that's the net ionic equation. CuCO3 plus 2H plus producing Cu2 plus H2O plus CO2. You follow? Question. Before we go with the redox, so the last type of the reaction, and after we're done with this one, we're going to take a break. It's something to do with the redox, which is just the acronym of reduction oxidation reaction. And as I told at the beginning, that's electron transfer. But for you to ask, how do we know if there's a transfer of electron? You have to learn the concept of oxidation number. So for a monatomic ion, the actual charge of the atom or a hypothetical charge assigned to an atom in the substance using simple rules. So oxidation number, some sort of an arbitrary number that you assign to a given element depending on what form that element is. Now, if that element, okay, exists in elemental form, the oxidation number of an atom is 0. So this applicable to hydrogen, oxygen, fluorine, the solid sodium, the solid potassium, Fe, iron metal, okay, gold, silver. So the one that it exists as an element, its oxidation number is equals to 0. Now, if that element is in ionic form like Na plus, okay, F minus, Cl minus, whatever the charge that you have there, that is the oxidation number. So the oxidation number of an atom in a monatomic ion equals the charge on the ion. And sometimes it is based on the periodic table. So all group 1A, when they form into ions, will give you +1. All group 2A, when they form into ions, they give you plus 2. If you have group 7A, when they form into ions, it's 7 minus 8, giving you negative 1. And if it's group 6A, like oxygen, okay, 6 minus 8 will give you negative 2. You subtract it with 8. And you will learn about that before the end of our session this semester. What's this 8 thing? Or the so-called octet hole. Now for oxygen, okay, if it's found in a given compound, most likely its oxidation number is negative 2. The only exception is if you have the so-called peroxide, wherein the oxidation number is equals to negative 1. Hydrogen, on the other hand, its oxidation number when it is combined with another element in the compound is positive 1, but if it's in a binary compound with the metal, it is negative 1. So for instance, if you have water here, if I ask you to assign the oxidation number for each of these elements, so this is negative 2, this is plus 1. So if you're going to add the oxidation number there, plus 1 times 2 will give you plus 2, and then you add it with 1 times negative 2 plus negative 2, so you get the 0. And this 0 represents your charge. And in water, the charge is equals to 0. Maybe it's not yet clear to you, but it takes a practice to answer questions like this. We will have some, don't worry. When we do to the redox reaction, we're going to assign all the elements involved with the respective oxidation number. So you will learn. Okay? Don't worry. Halogens. So these are the group 7A. So as I've told you, if it's 7A, you subtract it with 8, you have negative 1. So when you have halogens that is combined with other element, it always have a negative 1 oxidation number. You can only have a number other than what we call negative 1 if other element of the halogen above the periodic table or the other element is oxygen. So this happens when you have it like this. So in this case, your Cl is not negative 1. It's another oxidation number. So you're going to determine your oxidation number of chlorine here by just doing this what? Negative 2 and this is positive 1 and the charge is equals to 0. So you're going to find a number there plus 1 plus Cl plus negative 2 equals to 0. So what's the number that satisfies this expression? Your Cl there is positive 1. And as I told you, that's the statement there, except when the other element is another halogen above it in the periodic table or the other element is oxygen. The main important thing that you need to know here is look at the common or the one that's oxidation numbers already known. You assign that, and then when you add all those oxidation number, okay, the sum should be equals to the charge. That's the basis of this statement 6. The sum of the oxidation number of atoms in a compound is 0. The sum of the oxidation number of atoms in polyatomic ion equals the charge of the given ion. Let's try to have some example. Potassium permanganate is a purple colored compound. Potassium manganate is a green colored compound. So determine the oxidation number of the manganese in this compound. So I'm going to put here K M N O 4 K 2 M N O 4. So which one do we know the oxidation number? Which element do we know the oxidation number right away? The oxygen. It's always negative 2. Potassium, group 1A, when they become into an ion, it's plus 1. What's the charge that you have here? 0. So you could put here, so this is negative 4 times 2. So if I'm going to put here, so this is plus 1 plus manganese plus 2 times negative, not 2, 4 times negative 2. Where did I get the 4? Here. And I'm going to put it equals to 0. Why 0? Because the charge is equals to 0. There's no charge that you have here. The same thing that I have here. So I have a 2 times plus 1 for potassium, and then manganese that I don't know, and then 4 times negative 2 equals to 0. So if I have that, I have a plus 1 plus manganese plus, that's a negative 8 equals to 0. Here I have a plus 2 plus manganese plus negative 8 equals to 0. So rearranging this cell, you get what? Positive 1 plus negative 8 will give you negative 7, right? So put it on the other side. That means your manganese is positive 7. The same thing here. Plus 2 plus negative 8 will give you negative 6. So put it on the other side. That's the oxidation number. Analyze. Before we go on another example, let's try another one. What is the oxidation number of chromium in dichromate? So here you have a charge. So the way that you're going to do here, you know that oxygen is negative 2. So you have here 2 chromate plus 7 times negative 2 is equals to negative 2. So 2Cr plus 7 times negative 2 will give you negative 14. And then when you put it on the other side, that's negative 2 plus 14. So this becomes 12, right? Divided by 2. So each chromine here has a charge of positive 6. And you can check it, okay? So positive 6 times 2 will give you what? Positive 12. And then on the other one, you have negative 2 times 7. That will give you negative 14. And if you do that operation, you have a net charge of negative 2, which is the charge. negative 2 negative is equals to. You can do it also here in the previous one. Okay, so 1 plus 7 give you positive 8 plus 4 times negative 2. So 8 minus 8 will give you 0. The same thing here. Plus 2 plus 8, okay, plus negative 8, that is also equals to 0. So I think I have one question about that. Determine the oxidation number of a certain element in a given compound. So now that we know that, we can determine if a given reaction is a redox. Because a redox reaction is a reaction in which there's a change in the oxidation number of the species involved in the reaction. Okay, so if we're going to look at the redox reaction, as I've told you, it's made up of two reactions, oxidation and then reduction. One part of which involves the loss of electron or increase in oxidation number, and the other part of which involves a gain of electrons or decrease in oxidation number. Okay? And I usually ask my student to know the so-called Leora and the Geroa. Leora is loss of electron. That means it's undergo oxidation and it's a reducing agent. Geroa is gain electron. That means it's undergo reduction. Oxidation means increase in oxidation number. Reduction really means reduction in oxidation number. And it's act as your oxidizing agent. So when we say oxidation, the half reaction in which electrons is lost, loss of electron, Leora. Reduction is gain of electron, Geroa. Okay? The oxidizing agent, that's the species that oxidize another species and it is self-reduced. And the reducing agent is a species that reduces another species, it is itself oxidized. Now, there are different common redox reaction. There's a combination reaction, a decomposition reaction, a displacement reaction, and a combustion reaction. And the way that we're going to look at this is we look at the change in the oxidation number. Okay? So the first one that we have, combination reaction. So this is where two species become one. I don't know if you know the Spice Girls. They have a song, Two Becomes One. So if we're going to look at the reaction here, so we can assign the oxidation number. Sodium is an element, so that's 0. Chlorine is an element, that's 0. Sodium chloride, this is a -1. Chloride is this is a +1 for sodium, and chloride is a -1. So I can ask you, which is the one that is reduced? Which is the one that is oxidized? Anyone? Try to type. Because I can also ask you what is the reducing agent and what is the oxidizing agent. So these are the type of questions that we will ask you. So how do you know? Leora Geroa. What happened to the sodium there? It becomes positive. Its oxidation number increased. So we could say that's the one that's oxidized. And since it is oxidized, most likely that's the one that is the reducing agent. Chlorine, on the other hand, from 0, it becomes -1. There's a reduction in the oxidation number, so that's the one that is reduced. You can just say chlorine. And that serves as your oxidation agent, oxidizing agent. Geroa, gain electron, reduce, and oxidizing agent. So that's a combination reaction. We could say A plus B producing AB. Now the reverse of the combination reaction is decomposition reaction. You have AB producing A plus B. And again, the same thing happens. So this is 0, this is 0. You assign the oxidation number. This is -2, and this is +2. So which one is oxidized? The one that oxidized is oxygen because it becomes more positive. The one that is reduced is mercury. From +2, it becomes 0. But you seldom ask question which is oxidized and reduced in a decomposition reaction. You just ask maybe for the oxidation number here. So as you could see, there's a change in the oxidation number, so that means this is a redox reaction. So the third one, we could put it as AB reacting with C to give you CB plus A. And again, you have to assign the oxidation number. So you expect this to be 0, -1, +1. This is 0, okay, +2, -1. So as you could see here, one of the element is not changing its oxidation number. But you can be asked the question here, which one is oxidized and which one is reduced? You can ask what's the oxidizing agent and what is the reducing agent. So which one is oxidized? Is it zinc or hydrogen? So the one that's oxidized is zinc. Okay, 0 to +2. The one that is reduced is H. In terms of oxidizing agent, you have to write the whole thing. Okay, so zinc is the reducing agent. HCl is the oxidizing agent. Again, what's the guide? Reducing agent. You could say Leora. The one that is oxidized serve as the reducing agent. The one that is reduced serve as the oxidizing agent. Geroa. Okay? Now, the special type of reaction is the so-called combustion reaction. And usually it involves oxygen. But I'm going to show you that this is also a redox reaction because you have here 0, 0 as the oxidation number of both Fe and oxygen. And here, what do you have? -2. So based on this -2, what will happen? So -2 times 3, that will give you +6. And you have there 2, +6 divided by 2, this is +2. F3. And the one that is oxidized, or the one that undergo oxidation, is Fe, and the one that undergo reduction is oxygen. And the one that is the oxidizing agent is your oxygen, and the one that is your reducing agent is Fe. Usually, the one that is the reducing agent is a metal, and the one that is an oxidizing agent contains an oxygen. That's another way to know them.
Can you repeat that, please?
Yep. Yes, Talina.
Can you repeat what you just said about the other way of finding?
Usually, the reducing agent that you have are the metals, and the oxidizing agent that you have is the one that contains what we call oxygen. If oxygen is not there, then usually it's the other one that is not metal.
Thank you.
That's the simplest way to remember them. But the thing that I asked you to do is the Leora and Jajero one thing. I think that's the one that will really help you. Now, the last part that we have here, but I'm not going to give you in your quiz, the balancing simple redox reaction. Maybe in Gen Chem 2, you will come back to this one. So the way that I'm going to give you, I just give you a reaction and maybe ask you for the oxidation number. Okay? Because the balancing would involve making sure that in addition to having the same number of elements on both sides as the typical balancing chemical equation is, you have to make sure that there is the same number of electron exchange from the one that is oxidized to the one that is reduced. So the way that you're going to look at here is just assign the oxidation number, and then from that you will see the difference. So what does it mean here? There's two electrons when zinc was oxidized, but only one silver when it was reduced. So what are you going to do? You have to make sure that they're going to be balanced. So you divide them into half reactions. And as you can see here, there's two electrons here, there's only one electron here. So what you're going to do? You're going to multiply this by 2 so that this becomes 2 electrons. And in this case, there's already the same amount of electron that is being exchanged. And all you need to do is combine the two and you have the balance redox reaction. But I'm not going to do that at this portion because there's just too much that you need to cover. Okay? And although there's one that it says here, I promise I'm not going to include balancing of redox, at least for the chapter quiz and the final exam for Gen Chem 1. But you will encounter this again in Gen Chem 2. So as I promised, we have a break because I think I cannot what we call go over on this. So 15 minutes, fine with you? I just need to rest my voice. And prepare your calculator because this is calculation, the one that we have. So 15 minutes. So what time do we have right now? There you go. So let's resume our class. And this part is the one that involves calculation. Now, we're dealing with solutions because that's where most often the chemical reaction takes place. one solution added to another solution to form some product. That's the basis of your experiment 4, where you have barium 2 plus reacting with sulfate, giving you barium sulfate. So what really happened is you have barium chloride, you react it with sodium, no, not really sodium sulfate, but a sulfate containing compound. And this is the one that formed. And based on that reaction, you determine how much sulfate that you have here based on the amount of barium sulfate that formed. But before we go on that type of calculation, we go to the simplest expression or expressing units of solution, and that is molarity, denoted by big M. So that's moles absolute per liter of solution. So if you're going to look at the molarity, it's just defined as moles absolute per liters of solution. So here you will see now the importance of the discussion that we have in chapter 3. Because if you don't know how to get or determine the moles of a given substance, then it's going to be harder for you to do the calculation. So, given the thing, usually when we prepare a solution, we express it in molarity or molar. The way that you do is you add the measured amount of solute to a volumetric flask, then add water to bring the solution to the mark on the flask. So if we want to prepare a solution with a given concentration in molarity, okay? So whatever the volume that we end up preparing, all we need to do is determine the mass. But before we determine the mass, usually concentration equals to moles over liter. So before you do that, that's really mass over molar mass. Okay? Now, another way of preparing what we call solution is if you already have the so-called stock solution. So stock solution are solution of higher concentration. And you want to prepare a solution of lower concentration, you do dilution. And in doing dilution, what you have is just preparing a solution of lower concentration from a higher concentration. So the one that we use here is M1B1 equals to M2B2. In most of the book, this is like this. So most likely this is the higher concentration and this is the lower concentration. So you're given the concentration there and the final volume, and then you're given the initial concentration and determine how much volume that you need to prepare a new concentration out of it. Whatever the units, you'll just cancel out. So if it's ml or liters, it will just cancel out. So if you're going to look at the molecular view of this dilution, okay, both of them would just contain what? If this is moles per liter times liter, and this is also moles per liter times liter, if you do the calculation on both sides, you're just going to have the same what? Moles. And this is depicted here. So this could be your C1B1, and this could be your C2B2. But if you're going to count them, okay, the number of the Cl2 here is just the same on both sides. What's the only difference? You have higher volume, at least with this one, compared to this one. So this is a little bit concentrated because the amount or the moles of your substance is in a little volume or a smaller volume compared to the one that you have here. The amount, but at a much larger volume. But if you're going to count the item that you have there, they're just the same. How many you have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the concept of this so-called dilution. Okay? So diluting a solution quantitatively requires specific glassware. And again, this is what you call a volumetric plus. Usually, you dissolve first your solute, transfer it quantitatively, and then add liquid until you see that line there, giving you the exact volume of that glassware. So let's try to do calculation involving this, because this is one thing that you need to know. If you cannot solve calculation problems in molarity and dilution, that is a strong enough evidence for me that you're not going to pass the course. But let's try to do it, okay? Because this is one thing that each of you need to know. Although this will be repeated in Gen Chem 2, okay, but at that level, you're going to include other concentration units. So let's try to do the problem here. So you place a 1.52 grams of potassium dichromate into a 50 ml volumetric glass. You then add the water to bring the solution up to the mark on the neck. So you are asked what is the molarity of K2Cr2O7. So you list down the given. What do you have? Mass, volume, and not directly, but you can get molecular mass. You have to find the molecular mass of this. And you should know how to do this because you have done chapter 3. Okay? So the molar mass of your potassium dichromate would be around 294 grams. How did I get this? I add all of the element in the given material. That clear? Okay. Now, what is the one that's being asked? Molarity. So if you're going to look at the equation, molarity is equals to moles over volume in liter. But you can break this down to mass over molar mass over volumes in liter. And if you do that, you will have what? 152 grams divided by 294 grams per mole. I can convert this 50 ml into liters. So for every 1000 ml, there's 1 liter. So I can, and what do you have? Anyone? If you do the calculation, I get 0.103 molar. I just follow the significant figures that is given there and express it in my final answer. So what do you think? You can answer questions like this? Question? Don't be shy. Let's try another one. A solution of sodium chloride used for intravenous transfusion or physiological saline solution. It has a concentration of 0.154 molar NaCl. So you're asked how many moles of NaCl are contained in 500 ml of physiological saline and how many grams of NaCl are in 500 moles of solution. So you can put the equation and then from that you can determine which one is given. So you're given the molarity, you're given the volume, so you can get the one that is being asked, which is in this case moles. And once you will be able to get the moles, you can just get the mass by just multiplying it with the molar mass of the NaCl. So that's how the problem will be solved. So if you're doing the math, so this will become what? 0.154. So that's a moles per liter. Cross multiplication, it will give you 500 ml divided by 1000 ml per liter. Now look at the unit. So ml, ml, and then liter over liter. So you will have here the unit that is equals to moles. And that would be equals to what? 0.154 times 500 divided by 1000. So I have what? 0.077. Excuse me. And the next thing that I'm going to do is I need to get the molar mass of NaCl. So from 0.0770 moles of NaCl, I have 1 mole of NaCl per 55, no, 35 plus 23, 58.4. And I have here 0.77 times 58.4. So that will give me around 4.49, which I can round up to 4.50 grams. Analyze. So those are the type of questions that will be asked on your chapter quiz. So I give you sample in what we call molarity question. So the next example that we have is a dilution question or a dilution problem. So in a dilution problem, a saturated stock solution of NaCl is 6 molar. How much of this stock solution is needed to prepare 1 liter of physiological saline solution, which is 0.154? So we will have a C1 equals to B1 and then a C2 equals to B2. So we can assign this as the C1 and this one we can assign as the C2 times the B2. And all we're looking for is the B1. So if we're going to rearrange this one, we just divide both sides by C1, leaving you the B1, the one that you're looking for on one side. So if we have that, we will have 0.154 molar times 1.00 liter divided by 6.0 molar. So you can what we call cancel it out. So the answer that you have there is in liter, although you can convert it further to ml. So 0.154 times 1 divided by 6 I have 0.0257, which if I'm going to convert to ml, so that's 1000 ml per liter. That means I'm going to get 25.7 ml of that 6 molar and then dilute it to 1 liter. So I will get a concentration of 0.154 molar. Analyze. Question? Before we go with the quantitative analysis. So in the quantitative analysis, this is a determination of a substance or species present in a given material. In experiment 4, you did, or you're supposed to do, gravimetric analysis. So this is a type of quantitative analysis in which the amount of a species in a material is determined by converting the species to a product that can be isolated completely and weighed. So what do you have in experiment 4 if you started already? You reacted with barium, some unknowns that contains your sulfate. And what happened is they're going to form barium sulfate on it. And what you're going to do is you determine how much barium sulfate that you have here for you to determine the amount of sulfate in a given sample that you use in the reaction. So since it's based on the mass, we call it gravimetry. Okay? So the way that you did the reaction there is, let's say you have a barium nitrate reacting with, instead of potassium chromate, you use sodium sulfate. Okay, so when you add the two together, you will form the precipitate because it is insoluble, the barium sulfate that you form. So if I'm not mistaken, you have barium chloride reacting with a sulfate containing material. Okay, so what you do, the precipitate that you're going to do, you're going to dry it and then you're going to weigh it. You even ignite it. And during that time, you digest it, okay? So that the size of the particle will increase. So what happened there, after you dry it, you weigh it. So once you know the amount of your barium sulfate, you can get how much sulfate you have in your unknown. Because there's a 1:1 mole ratio on it. So that's how experiment 4 will be done, okay, if you have not done it yet. Because I see some of you submitted already the lab report. So let's try to have some problems similar to that one, but instead of barium sulfate, we have silver carbonate. Oh no, silver compound. It's not silver carbonate. So it says here, you have a soluble silver compound that was analyzed for the percentage silver by adding sodium chloride solution to precipitate the silver ion as silver chloride. So if 1.583 grams of your silver compound gave 1.788 grams of silver chloride, you are asked the mass percent of silver in the compound. So if you're going to look at the reaction here, so you have some silver ion or silver compound that when you add with chloride, let's say sodium chloride, it formed silver chloride. Okay? So you found out that this is around 1.788 grams. And the silver compound sample that you have, it's the whole sample, it's not only silver, is 1.83 grams. So what you want to do, by getting this information that you have here, you want to determine the exact amount of the silver there and then divide it with the amount of the sample so you can determine the percentage of silver. So how are we going to do that? Maybe we can start with the amount of 1.788 grams of silver chloride. And then what we're going to do? We determine the number of moles of silver chloride. So for every 1 mole of silver chloride, we divide it with the molar mass of the silver chloride. So 143.32 grams. Where did I get the 1.32 grams? That's silver plus chlorine in your periodic table atomic mass when you add them. And then from that, you know that for every 1 mole of silver chloride, how many silver? How many moles of silver you have? One. Okay. And then from that, okay, you're able to get that for every 1 mole of silver, you have the molar mass or the atomic mass of your silver, which is 107.9 grams. So you may ask, where did I get this? The silver molar mass. Where did I get this? That silver plus chlorine molar mass. And if you're going to look at this, whatever the answer there, that's the mass of your silver, which is the mass in your silver sample or the sample containing the silver. So if you're going to look at the unit, we can cancel, and we can cancel, we can cancel, leaving you with the silver. And if you're going to do the calculation, how much do you get? 1.346. So this is the amount that we have here of silver based from here. And to get the percentage, we just have 1.346 grams of silver over 1.583 grams of the sample. And then you multiply it by 100, giving you 85.03. Analyze. So you're going to do this type of calculation in your what we call the lab report. And if I'm not mistaken, I think I have some sample calculations also during the discussion. So that's just one quantitative analysis. Okay, that's based on what we call the mass. That's what we call gravimetric. Now in experiment 5, there's another quantitative analysis that you're going to do, and this has something to do with what we call titration. And titration is a volumetric analysis, which is based on volume. So in the titration, what you have, you have a procedure of determining the amount of substance A by adding carefully measured volume with known concentration of B. So you have mole of A reacting with mole of B. So once you know their stoichiometric ratio, once you know how much moles of A you use up, you can determine mole of B. How do you get the moles of A? So it's based on the molarity times uh, liters in volume that you have. Because moles over liters times liters will give you the number of moles. Okay? Now, the way that you do the experiment 5 is the moles of B that you have there, the standard that you use, you can get it from mass over molar mass, right? Mass over molar mass will also give you the moles. So once you determine this one, once you determine this one, you get the volume, you can determine the exact concentration of a given substance. That's the basis of your experiment 5. So in the titration that you have here, you're going to add. So this is your initial volume. So you're going to add until you see a color change. So that's your final volume. So the difference between the two, that's the volume. If you know the concentration, you multiply it with the concentration. If it's with the standard, you know the mass of the standard and it's smaller mass. So what you're going to do, since the one that you're being asked here is the concentration and what you have is the volume, so all you need to do is divide it with the volume so that you can determine the exact concentration. Okay? So volumetric analysis is useful. It's a type of quantitative analysis based on titration. You use the volume. So for instance, if we have a reaction here, zinc sulfide reacts with hydrochloric acid to produce hydrogen sulfide gas. So given this reaction, you're asked how many ml of 0.052 molar HCl are required to react with 0.392 grams of zinc sulfide. So you have to look at this and this. What can you say about the reaction? What's the stoichiometric ratio? Hmm? It is what? Is it 1:1? Usually it is. For every 1 mole of zinc sulfide, you have 2 moles of HCl. So what are you going to do is you're going to look at the given reaction that you have. So in doing that, you can start with what? The zinc sulfide mass. And then, what are we going to do? We're going to get the molar mass of the zinc sulfide. So we can determine the moles of your zinc sulfide. So we could say, determine zinc sulfide molar mass. It's 97.45. So for every 1 mole of zinc sulfide, you have 97.45 grams. So I get the 97.45 by adding zinc and sulfur. Okay? So in this calculation, you already have the moles of your zinc sulfide. So the next thing that you're going to do is, what's the equivalent of zinc sulfide with HCl? So for every 1 mole of zinc sulfide, I have 2 moles of HCl. Okay? So what's the next thing that I'm going to do? Once I get the 2 moles of HCl, the moles of the HCl, the next thing that I'm going to do is I'm going to get the equivalent, the molarity that I have here, because I'm asked what's the volume that I have here. So I could put here, for every 1 liter, I have 0.0512 moles. Remember, molarity is moles per liter. But since I want the moles to cancel out, so what did I do? 1 liter over 0.0512. And once I have the calculation here, since the one that's being asked is ml, I can still continue here, but this time, for every 1,000 ml, I have 1 liter. So cancel the one that can be canceled, moles over moles, moles HCl's over moles HCl here. So I end up with liter over liter, so I end up with an ml. So if I'm going to do the calculation here, 0.392 divided by 97.45 times 2 divided by 0.0512 times 1,000, what did I get? 0.392 divided by 97.45 times 2 divided by 0.0512 times 1,000, I get 157. Are you there? Anyone? Are you still with me, the four of you? So that's how you solve the problem. As I've told you, it's all about dimensional analysis. So it's just arranging them from the beginning, that you're whatever values that you're given until the end, to the value and volume, and the unit that you need. So another one that we have here, this is the last one. So it has something to do with the hydrogen peroxide. So this is the typical reaction, and you are asked what is the mass percentage of H2O2 in a solution if you have 57 grams of solution requiring 38.9 grams or ml of 5.34 molar KMnO4. So how are we going to solve this? I'm going to use a whiteboard, as we mentioned here. So if we're going to look at the materials that we have, so what are the one that is given? So if we have the whiteboard, we can have the, okay, 57.5 gram solution. H2O2 solution. And then you're also given the volume, 38.9, 0.534 KMnO4. So what is being asked here is the percentage of H2O2. in solution. So how do we start here? Maybe I can start with the 38.9. So I have 38.9 ml. I convert it to liters. And then what will I do? I'm going to multiply it with the concentration. So I have here 0.534 moles per liter of KMnO4. So when I do it here, this is already in the unit of moles of KMnO4. So what will I do? I'm going to multiply it with the stoichiometric ratio. So if you're going to look at the stoichiometric ratio, I have to use this. I have moles of KMnO4. So for every 2 moles of KMnO4, there's 5 moles of H2O2 that reacts with it. Because that's the one that I'm going to use in the next one. Okay? So for every 2 moles of KMnO4, there's 5 moles of H2O2. So what's the next one after I have there? Since during this time of the calculation that I have, I already have the moles of H2O2, I can determine the mass of H2O2, which is around 34 something, 34.01. So when I do the calculation here, I will get the grams of H2O2. And what will I do? I'm going to divide it to the grams of the H2O2 solution. So if we're going to do the number here, 38.9 divided by 1,000 times 0.534 times 5 divided by 2 times 34.01, I get 1.766 or 1.77 grams. So what will I do with this? I'm going to divide it with the 57.5 grams of H2O2 solution and then multiply it by 100. So I end up with a 3.07 percentage. And usually that's the percentage of your agua oxinada. Okay? Now question to the four of you, from the four of you. Question? Talina, Andrew? Oh, there's somebody has a question there. No, no. Hamsira, Jelisa. So I have not returned the experiment 2 and 3 because I'm waiting for everyone to submit them. So I can just grade them one time. But the thing that I do is, if ever you have question, my only request is, if it's related to the exam, please don't send that email near the deadline. Okay, because I already see some students were doing fine. Okay, uh, and all I want to do is, we still have enough time if ever some of you mess up some of the quizzes. So all I need is everyone to be in touch with me. So I would suggest you ask it a day before at the latest, because that's the reason why I set it later on the week. Because one student, I think, asked me 9 o'clock on Friday night. Some he just the thing is, you don't email me if I can ask you a question. Email me right away the question, because it will prolong the exchange of communication if you email it like that. Because the student email, what's the email? Oh, can I email you some question? That's the email that he asked. And then I wasn't able to write it. And the next email that he had to me, oh, I'm going to drop the course. So I was surprised, because when I look at the grade, she's third among the scores in the three quizzes that we have so far. Okay. So I told her, okay, so this is your performance. This is the score that you have, because the rule that we have is what? It's always over the highest. Okay. If the highest is really so high, there's still some adjustment that we're going to do. So I told him, based on this thing, you're going to get a grade of 90, because I think her score is 36 and the highest is 39. So it's really a good one. And then I answered her during